Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the mathematical definition of continuous random variables. This mathematical definition can be a little bit intimidating the first time you come across it, but we're going to connect it to the way we actually use random variables in terms of probabilities associated to those random variables, so hopefully you will see that it's actually relatively intuitive. The goal is that if in the future you open a probability theory book and you come across a phrase such as the sigma algebra of Borel sets, that you don't just panic and close it and run away, but that you actually understand that these mathematical concepts that can be a little bit obscure are just set up in a way that enables us to describe a continuous random variable using probabilities. Let's get to it. I'm checking that we're recording because a moment ago I actually did this whole video without pressing record, which was kind of frustrating, but I am. So let's do this. We're going to talk about the mathematical definition of continuous random variables. Ultimately, our goal is to be able to model physical quantities that can be interpreted as being continuous, such as length, mass, or time, as continuous random variables when those physical quantities are uncertain. That's what we want to do. Set up a mathematical framework that enables us to describe continuous physical quantities in terms of random variables. The notation is as usual. If things don't have a squiggly line or a tilde on top, they are deterministic. They have a fixed value. If they do have a squiggly line on top, if they do have a tilde on top, that means that we're modeling them as random variables. So we have to describe them in terms of probabilities. Okay, they do not have fixed values. Okay, so what is a random variable? Depends whom you ask. If you ask a data scientist, they will tell you that it's just a variable that they describe using probabilities that they can estimate from data. But if you ask a mathematician, you'll get a very different answer. They will say that it's a function from a sample space in a probability space to the real numbers. And they may even say that that function has to be measurable. These two perspectives sound extremely different, but as it turns out, this mathematical definition is just built so that we can use probabilities to describe random variables, and in particular so that we can use probabilities that connect multiple random variables. We'll talk more about that later on when we consider models where we have several random variables and we model their joint distribution. But just so that you know that that's kind of like an ulterior motive for setting up all of this mathematical framework. Anyways, let's remind ourselves how we defined discrete random variables mathematically. Mathematically, a discrete random variable is a function from a sample space within a probability space to a discrete set of values. In this case, there are only three: A1, A2, and A3. Those are the three possible values that the random variable can take. So this function from the sample space maps every outcome to one of those values. So within this set of outcomes, all of them are mapped to A1. Within this one, they're all mapped to A2, and within this one, they're all mapped to A3. And what we explained is that at the end of the day, if you want to describe and manipulate the random variable, you actually don't need this part. You don't need to even know what the probability space is, as long as you have access to the probabilities that the random variable is in each of these events. Okay, so maybe let me erase all of this. As long as you know the probability that the random variable is in this event, which is exactly equal to a probability that the random variable is equal to A3, and also the probability that it's equal to A1, and also the probability that is equal to A2. As long as you don't know those probabilities, you can just manipulate the discrete random variable using those probabilities. You can forget about the probability space. Those probabilities form what we call the probability mass function, the PMF, and that's what we actually estimate from data directly. This is only possible because when we define the discrete random variable as a function from this sample space of the probability space to the reals that maps to a certain discrete set, we impose that each of those preimages of all the outcomes that map to each of these individual values are all in the collection, which is just a fancy way of saying that they are assigned a probability, so that we can talk about the random variable having that probability. Okay, and this is how we defined discrete random variables mathematically. Now the key question is, can we do the same for continuous random variables? Can we just define the probability that the continuous random variable is equal to each of the possible values that it can take, and then just reason with that, okay, which is what we do with discrete random variables? The answer is no, we cannot, for two reasons. Well, I guess we can explain the reasoning behind this in two ways. There's an intuitive reason and there's a mathematical reason. Intuitively, if we want to model a physical quantity that is continuous, the probability that it takes individual points, the individual values, should be zero. Maybe, to gain some intuition, think about what is the length of a single point on a line. It's zero, right? What is the mass of a single point in an object? It's zero. What is the area of a single point on a 2D surface? It's zero. Well, in the same way, if you have a continuous uncertain quantity, the probability that it's equal to a single specific point should also be zero. This is just intuitively. Mathematically, the reason is that if we assign non-zero probabilities to every point on the real line, or even on an interval of the real line, we're going to have a problem, because the real line, or any interval of the real line, contains uncountably infinite points. So we assign non-zero probability to each of them. When we consider the total probability that we have assigned, it will explode to infinity. We won't be able to keep it bounded so that total probability is equal to 1. So that we cannot do this mathematically, which connects to the intuition that if something is continuous, you shouldn't assign non-zero probability to every point in a continuous interval. So instead, we have to come up with an alternative strategy. We're not going to be talking about the probability that the continuous random variable is equal to specific points, because that's going to be zero, but we can talk about the probability of the random variable being in intervals. And that's the way we describe continuous random variables, in terms of the probability that they belong to intervals of the real line. So here, for example, we're going to have a random variable a. We want to be able to talk about the probability that a is in a certain interval I1 or a certain interval I2 for any choice of intervals. If we define the random variable as a function from a sample space to the real line, then we can think of the pre-images, which just means the sets of outcomes that map to each of these intervals. These are the sets of outcomes that map to I1. These are the sets of outcomes that map to I2. Let's take a look at an example. Omega 1 is in the pre-image of I1, so it maps to some point in I1. Omega 2 and omega 3 are in the pre-image of I2, so they map 2 points in I2 through the random variable. So you can imagine basically the random variable mapping this to some point in I1. This is the random variable, which is this function, and this guy, the same random variable mapping these 2 points into I2. Now, if we want to be able to talk about the random variable being in these intervals, we need that the probability of these pre-images be well defined. And that's exactly what we impose in our mathematical definition of continuous random variables. So we define, actually I had a better picture here of a omega 1, a omega 2, and a omega 3. But like this, you got to see my squiggly lines. Okay, so the mathematical definition of a continuous random variable. We have a probability space, has a sample space, a collection of events, and a probability measure P. We define the continuous random variable as a function from the sample space to the reals, which has to satisfy the following. For any interval here between some 2 points a, b on the real line, if you consider all the outcomes that map into that interval, which we call the pre-image of the interval, okay, those are outcomes in the sample space, the set of those outcomes has to belong to the collection so that it's assigned a probability by the probability measure, and we can actually talk about the probability that the random variable belongs to that interval. If that is true for any possible interval, we call this function measurable, and we have a valid random variable. You might have realized, if you're looking carefully at the slides, that this is an F instead of a C. The reason for this is that I used to use the more traditional notation for the collection of events. If you go to a book on probability theory, typically they will not call this a collection of events, they will call this a sigma algebra, because the collection of events satisfies the conditions that we already discussed when we introduced probability spaces. And they use this weird F usually to denote the collection. At some point I decided that the name sigma algebra is just scary for no good reason, and I wanted to call this thing a collection, so I changed all the F's to C's, but I forgot to change that one. Anyways, the definition that I just gave you does not preclude us from having a countable number of points that have non-zero probability. You could actually do that. But then we wouldn't have a continuous random variable. We wouldn't call this random variable continuous. It would still be a valid random variable. But typically when we talk about continuous random variables, we assume that each point has zero probability. Okay, so now the good news is that we have a mathematical definition of continuous random variables that enables us to talk about the probability of the random variable belonging to intervals. The bad news is that we're saddled with this underlying probability space that we don't really want to manipulate. So now let's think about what if we want to describe the behavior of the random variable. For example, we want to say that the random variable is in a certain union of intervals. That means that it's either here or here. With the probability measure, we can actually compute that, right? What do? We say, okay, what is the preimage of the union? That preimage of the union, if you think about it, has to be the union of the preimages. Why? Because for a point to be here, there must be a point in one of these two guys that maps to it, right? So very quickly, you're going to realize that the preimage of the union is equal to the union of these two preimages. Now, though, that union of the two preimages has to be assigned a probability just by the properties of the collection of a probability space, where if you assign probabilities to individual events, you also have to assign a probability to their union. So that's cool, right? Like that probability is well defined, but we have to go to the underlying probability space to look for it. Very annoying. However, then you might realize that if these guys are disjoint, then these guys also have to be disjoint. And you can see this very easily by contradiction. I'm going to clean up this a bit because it's starting to get very cluttered. You can see this by contradiction. Imagine that you have a point, imagine that these guys are not disjoint, that there's a point that is in the preimage of I2 and the preimage of I1. Then the function A, this random variable that we're considering, is going to map this to both I1 and I2, which means that I1 and I2 could not be disjoint. So by contradiction, we have proved that if these intervals are disjoint, then their preimages that contain the outcomes that map to each of them are also disjoint. Why is this super useful? Because the probability that the random variable is in here, in the union, is equal to the probability that it's in the union of the two preimages. But if the two preimages are disjoint, then that's just the sum of the probabilities. And those probabilities are the probabilities that you are here, which is the probability of the random variable being in I1, or here, which is the probability of the random variable being in I2. So we can express the probability that the random variable is in the union of the two intervals just in terms of the probabilities of the random variable belonging to each of the intervals. We don't need to go back and look at the probability measure as long as we have the probability of the random variable belonging to any interval, which we'll see how to encode a bit later on, but at least this liberates us from the underlying probability space. Just to be a bit formal about this, you can prove this for any union of n intervals, or even a countably infinite series of intervals. Let's see why. Well, we want the probability that A is in the union. That is the probability of this event that contains all the outcomes that map into the union. But that's just the probability of, that's just the event of belonging to the union of the, to the pre-image of this union of intervals. And we saw that that pre-image of the union of intervals is just equal to the union of the pre-images. And now we realize that if these guys are disjoint, then their pre-images are disjoint, as we explained. So this is just a sum of the individual probabilities. And now these individual probabilities, we can express them in terms of the probability that the random variable is in each of the intervals. So again, we need the sample space, the probability space for the proof, but at the end of the day, if we want to compute the probability that the random variable is in a union of intervals, we just need the probability that it's in each of the individual intervals, which liberates us from the underlying probability space. Okay? It turns out that, in case you're worried about notation and so on, if you want to, because of the fact that we're considering continuous random variables, if you have a closed interval, by what we just said, you can express this as the probability of the random variable being equal to A, the probability of the random variable being equal to the open interval from A to B, and the probability of the random variable being equal to B, because the union of these guys, which are all disjoint, is equal to the closed interval. Okay, but as it turns out, the probability of being equal to each individual point if the random variable is continuous is just 0. So this is just going to be equal to the probability of the open interval. This was just to apply what we just learned about how we can manipulate the random variable in terms of probabilities that just refer to intervals as opposed to the underlying probability space, but also to tell you that you needn't worry about whether an interval is closed, open, and so on, because the probability of being at precisely the border is always going to be 0 if we're considering continuous random variables. Okay, so technically, you might be wondering, okay, but the way you have defined continuous random variables, we can only talk about the random variable belonging to a union of countably infinite sets, okay? That's the only thing we can do. So I would encourage you to think of a set that cannot be expressed as a union of countable intervals. And in fact, they do exist. So these sets that can be expressed as a union of countable intervals are called Borel sets. And it turns out that there exist non-Borel sets. So this might be a little bit problematic. You might be like, okay, so what if I want the probability of being in a non-Borel set? Well, unfortunately, it won't be well defined. However, these sets are completely pathological from the practical point of view, and you will never, ever encounter them in data science, and even if you're doing mathematical research, unless you do very specific measure theoretical research. So we don't care about this. We live by just defining random variables as belonging to Borel sets, which are these unions of intervals. In case you come across that phrase that I mentioned at the beginning in a probability theory book, these Borel sets actually form a sigma algebra, which means that they form a valid collection where if you have a union of Borel sets, it's also a Borel set, a complement of a Borel set is also a Borel set, and so on and so forth. So they are a valid collection, just so you know. And remember that sigma algebra is this fancy word for these valid collections that satisfy the requirements of a probability space. Okay, so our conclusion is that we can describe continuous random variables in terms of the probability that they belong to any interval. And this connects our two perspectives on random variables. Okay, we define them mathematically as functions, but at the end of the day, these functions have to satisfy this requirement that the probability that they map to intervals is well defined. And then we saw that because of that, we can just reason about the probability of the random variable belonging to any interval. We don't need to refer to the underlying probability space for anything. So we can directly estimate from data the probability that the random variable is in different intervals and reason with that, just like the data scientist wanted to. You might be thinking, okay, but keeping track of the probability that a random variable is in any interval, that sounds pretty complicated. We will see that there are two tools that make that relatively easy. One is the cumulative distribution function, or CDF, and the other is the probability density function, or PDF. We will explain them in detail in the next videos. And that's all I got. I hope that now the definition of continuous random variables doesn't seem as scary. Thank you very much.